On a recent homework assignment, I asked people to check and see if the Hermite interpolating polynomial produces not only the correct function values, but also the correct slopes for the n equal 2 case. Now, everyone is in agreement that the function values and the derivative are correct at the first data point on our list, because that was easy. We will see that in just a little bit. Many people got lost in the algebra and came to the conclusion that the derivatives don't match at the other data point. This is obviously not right. We can make a little logical argument here. Imagine that you order the data in the usual way, Z0, Z1, Z2, Z3, with corresponding function values and also corresponding derivative values. Write out the Hermite interpolating polynomial. Everyone agrees that it interpolates the slope at x0. I claim that it's obvious that it must also interpolate the slope at x1. The reason for that is, imagine that you order the data in a different way. I'm going to call Z0 x1, Z1 x1, Z2 is x0, and Z3 is x0 with corresponding function values and derivatives. The data for which I'm building the Hermite polynomial in this second case is the same data that I was in the first case. So the polynomials have to be the same, but everyone agrees that the derivatives match for the first data point. So it must be true that P prime evaluated at x1 must be F prime evaluated at x1. The answer to the question is obviously yes from a logical point of view. Returning to the original ordering, I'm going to build the Hermite interpolating polynomial. Because the writing got so out of control, I decided to introduce some abbreviations. Capital delta is x1 minus x0. And when I write something of this type, I mean the divided difference based on z0 and z1, or for instance, the divided difference based on z1, z2, and z3, and so forth. As per the instruction, I'm going to figure these divided differences out, expressed in terms of the original x data, x's, f of x's, and f prime of x's. Now, as we've talked about before, in column k equal 1, if the row index is odd, I'm going to use one of my derivative values. So here, this is f prime evaluated at x0. This is f prime evaluated at x1. This one is a difference of two function values divided by x1 minus x0. So we now know column 1. By using our recursion formulas, I can figure out the divided difference based on z0, z1, and z2, also z1, z2, and z3. Once I know those, I can put them back in the recursion formula and figure out the divided difference based on z0, z1, z2, and z3, which I've simplified in this form. Recall, the reason that this is important to us is this number is the constant coefficient in my interpolating polynomial. This is the coefficient of the x minus z0 term, the coefficient of x minus z0 times x minus z1, and the coefficient of x minus z0, x minus z1, x minus z2. As I said, I'm going to write out everything in terms of x values, f values, and f prime values. So using the coefficients that we just stated, this is my Hermite interpolating polynomial. The issue that we were talking about, though, has to do with the derivative of it. The derivative of a constant is 0. The derivative of a constant times x minus x0 is that constant. The derivative of this coefficient is a constant, so I'll just write it down. I've got a product of two things. Using our formula idea from one of the other problems, I'm going to write down some things to add together. Each one of them is going to be this quantity with one of the factors left out. So if I leave that one out, I'll have x minus x0 there. If I leave that one out, I'll have x minus x0 to add in. I am not going to overly simplify things for reasons that will become clear shortly. The other term is this constant times the derivative of the product of these three things. I'm going to write down three terms. Each one of them looks like x minus x0 times x minus x0 times x minus x1, except I leave one of the factors off. If I leave that one off, I'll have x minus x0 times x minus x1. That's this term. If I leave that one off, I'll have x minus x0 times x minus x1, that one. If I leave that one off, I've just got two factors of x minus x0. The reason that I wanted to do that derivative problem that we had earlier in the assignment was it makes it very easy for me to write out the derivatives of these sort of product terms. So we figured out a formula for p prime at x, and I'd like to check whether or not this produces the correct slopes at x0, which it will, everyone agrees on that, and also at x1, which a lot of people don't agree with. So let's think about this. If I evaluate this derivative at x equals x0, then this number is 0, and so is that one. 0 times something is 0. This contributes nothing. If x is equal to x0, then that's 0, that's 0. Both of those are 0, and 0 times something is 0. The other term I have to add in is f prime 0. So p prime evaluated at x0 is f prime at x0 plus nothing, which is f prime at x0. Everyone who handed the problem in agrees on that. What about the rest of it? I've got to evaluate p prime at x1. This has no x in it. Pardon me. This has no x in it, so it just needs to be written down again. This term, if x is equal to x1, then this will be x1 minus x0 plus itself. That'll be 2 times x1 minus x0, or 2 times delta, as I'm calling it. So I'll have my coefficient times 2 delta. If x is equal to x1, then this is 0. That's 0. And I'll have a factor of x1 minus x0 times x1 minus x0. I'll have 0 plus 0 plus delta squared. So all I need to do now is algebraically simplify this, being careful not to make any algebra mistakes. For the rest of this, I'm doing my individual algebra steps, one little step at a time, to make sure I don't write something down that's not right. So initially, I'm just getting rid of the extra factors of delta. I'm algebraically simplifying. Split that second very ugly looking fraction up into pieces. F prime 1 times delta over delta is F prime 1 minus 2 F2 minus F1 over delta minus 2 F2 minus F1 over delta, plus I have F prime 0 times delta over delta, which is F prime 0. If you'll notice, some things are going to cancel out here. In particular, these fractions in the middle cancel out. Moreover, I have F prime at x0 plus F prime at x0, that's two of them, minus 2 times F prime at x0 plus F prime at x1. All terms have been accounted for. If you look at the first two terms, they cancel each other out, leaving you with F prime 1, which is F prime evaluated at x1. The Hermite interpolating polynomial, not only does it match the function values at x0 and x1, it matches the slopes of the f function at x0 and x1 as well. I hope this clarifies the situation on the n equal 2 Hermite interpolating polynomial problem. I'll talk to you again soon.